Today, we are going to build one of the most critical but kind of unsung heroes of the modern internet, an API rate limiter. Think of it as the invisible gatekeeper that keeps all our favorite services running smoothly and securely. And yeah, we're going to design one right from the ground up.
I'm pretty sure you have. That 429 error? It's not a bug. It's actually a feature. That's a rate limiter doing its job, telling you, hey, slow down a bit. So today, we're pulling back the curtain to design the exact system that makes that message pop up.
So you might be wondering, why can't a service just handle an infinite number of requests? Well, you know how a popular nightclub has a bouncer to manage the crowd? A digital service needs a gatekeeper for the very same reason, to manage the traffic and make sure everything is stable and fair for everyone. And the reasons for this are just so important. First up, security. It helps stop malicious attacks like denial of service. Then there's reliability. You don't want one rogue script to crash the whole service for everybody else. And of course, cost control. Every single request uses up server resources, and that costs money. Finally, it can actually be part of the business model where you offer premium users higher limits.
Okay, so we've established the why. Now let's get into the what. Every good engineering project has to start with a clear set of goals. So what are the absolute must-haves for our rate limiter? So here's the big picture. All the client requests come in, but before they even get a chance to talk to the main API servers, they have to get past our gatekeeper. The request only goes through if our rate limiter gives it the green light. Our entire focus today, it's on designing that little blue box right there. Our functional requirements are pretty straightforward, but they're going to drive every single decision we make. First, we have to limit requests per user within a set time window. Simple enough. Second, and this is a big one, it has to work across a whole cluster of servers. The count has to be shared. And third, when someone hits their limit, we absolutely must send back that standard 429 error.
All right, let's start with the most obvious, most intuitive approach. Think of this as our first draft. It's a simple algorithm called the fixed window. The logic here is really easy to grasp. We just chop up time into fixed blocks, let's say 1-minute chunks that start and end right on the clock. We just count how many requests a user makes inside that minute. When the clock ticks over to the next minute, poof, the counter resets to 0 and we start fresh. So how do we actually keep track of this? Well, the easiest way is with a simple hash table. You know, a key value store. The key is just the user ID, and the value holds two little pieces of info: the current request count and the timestamp for when that window started.
Let's walk through a quick example. Let's say our user, Christy, has a limit of 3 requests per minute. Her first request comes in. We create an entry. The second one, we just tick the count up to 2. The third, up to 3. All of those are allowed. But when she sends that fourth request inside the same minute, nope, the count is already at 3, so it gets rejected. Then, as soon as the clock ticks over, the start time and the count both reset, and she's good to go again.
It seems simple, right? And effective? And for the most part, it works. But in system design, the real fun is in the edge cases. And this simple approach, well, it has a pretty big flaw.
So, what's the problem here? Where can a clever user get around the spirit of the rule even while they're technically following the letter of the law?
And here it is. It's called the burst problem. Imagine Christy sends her 3 allowed requests in the very last second of a minute. The clock ticks over, her counter instantly resets, and boom, she sends 3 more in the first second of the new minute. So now she's just sent 6 requests in 2 seconds, double her rate limit, and that could easily overwhelm the server.
So to fix this, we need a smarter algorithm. Enter the rolling window. Now, instead of a fixed clock, this algorithm's window is relative to the current time. It asks, how many requests has this user made in the last 60 seconds from right now? This is much more accurate, but it means we have to store the timestamp of every single request. And as you can probably guess, that has some serious consequences for memory. And right here, we've hit a classic engineering trade-off. The fixed window is simple and super memory efficient, but it's got that nasty burst problem at the edges. The rolling window is perfectly accurate, but it comes at a huge cost. Storing every single timestamp for every user would eat up a massive amount of memory.
So the big question is, can we have our cake and eat it too? Is it possible to get the accuracy of the rolling window without that crippling memory cost? Turns out, yes, we can, with a really clever hybrid approach. Let me introduce you to the sliding window with counters. Now, instead of storing every individual request, we group them into smaller time buckets. So for, say, an hourly limit, we might track the counts for each minute. To check the limit, we just add up the counts of the last 60 of those buckets. It's a brilliant approximation that gives us the accuracy we need, but without that massive memory footprint.
And the impact on memory? It's just staggering. If you wanted to track 1 million users, the pure rolling window algorithm would need about 12 gigabytes of memory. But our optimized hybrid approach, it needs just 1.6 gigabytes.
Yeah, that's an 86% reduction in memory usage. And in the real world, that number translates directly into smaller cloud bills and faster performance. We get almost the exact same level of accuracy, we solve the burst problem, but for a tiny fraction of the infrastructure cost. It's a huge win.
Okay, so we've totally nailed down the core algorithm. But a real-world system has more moving parts. So let's zoom out for a second and look at a few other critical design decisions we'd have to make.
So here's a fundamental question. Who or what are we actually applying the limit to? We could limit by IP address, which is easy to do, but it can be really unfair. Just think of an entire office or a coffee shop sharing one single IP address. Or we can limit by an authenticated user, which is way more fair, but of course requires a login system. In reality, most large-scale services actually end up using a mix of both.
And how do we handle millions and millions of users? We use techniques like data sharding, where we split the user data across a bunch of different databases, so no single machine becomes a bottleneck. To make the system fault-tolerant, we use something called consistent hashing to distribute that data smartly, which makes sure that if one server goes down, the impact is minimized. We'd also want to set different limits for different APIs. I mean, creating a post is way more expensive than just reading one, so it needs a much stricter limit.
You know, at the end of the day, designing a rate limiter isn't just a technical challenge. It's a balancing act. It's all about finding that perfect line between protecting your service from abuse and giving your real, legitimate users the freedom and the performance they expect. So the final question is really, how do you decide where that line is drawn?